Wednesday, we'll go through this in detail. These will correspond with the parameters of some model we're typically going to be trying to learn, although this could be much more general. And we're trying to find the model which minimizes some cost function. So f is going to be some cost function. We generally want to find the minimum of this. Okay, and so I'll write. So right. So then the goal here is either going to be the min alpha in RD of this function. So I want to find, this gives me the value of the function at the minimum, or I'll say alpha star is going to be the R min of alpha in RD of this function. Right, so this is the argument that minimizes, so again, the argument is the argument that minimizes this function of alpha. So this will correspond with the model parameters, which minimizes this cost function. And we'll see how to set up the cost function and how to think about gradient descent within that paradigm on Wednesday. Okay, so the gradient descent is then an algorithm for doing this, and so it's going to start by initializing at some alpha 0 is going to be this alpha start that we get as part of our input. In the class, we'll just give you alpha start. I'll say here, start at this location. In practice, what do you do? And usually in practice, you're only given f, right? You're just given the model, or you're given data and you generate f, but you're not given alpha start. You could pick something arbitrary. Sometimes you run another algorithm or another guess to get you what's called a like a cold start or something, or like a warm start, where you start with something which is a good guess. If it's a good guess of what the optimum is, then you'd say it's a warm start. If it's an arbitrary guess, it'd be a cold start, and you want to get warmer, I guess. Okay, but there are various ways to do this depending on the context of the problems. But we'll be given this as the starting point of the model, and then we just kind of repeat some fairly simple step. We're going to set alpha k plus 1 is going to be equal to alpha k, then minus the sum step size times the gradient at alpha of k. Okay, and so when I write, so because this is going to be a d-dimensional vector, I don't want to use a subscript to say what point I'm at in the process, because that usually refers to the coordinate. So I'm using a superscript, but to make sure to try and differentiate this from being a power, I'm not taking it to the 0th power. I'm saying it's the 0th step. This is the kth step. This is the k plus 1 step. Right. So each step, I'm changing my set of coordinates from alpha k to alpha k plus 1. Okay, so this is not an operation, it's just some notational thing. And I don't really need the k there, it's just, in the code, you don't need to necessarily keep track of every step, although it turns out it's useful to do it for various reasons. It's just so we can discuss stuff more precisely. I know how to call something that happened at the k step. Okay. Okay, and you want to then just repeat this until usually you have some condition, and the typical, most common sort of condition is going to be that the norm of the gradient, this is the gradient we discussed, and I'll review the gradient in a second, but the norm of the gradient becomes less than some threshold. if this gradient is small enough, it turns out that means you're going to be pretty close to the solution. And then you, if that's the case, then you return alpha k. Okay, so this is the whole algorithm here. Or maybe it's, okay, so that's the whole algorithm, right? So it's very simple. Once you've initiated it, you just have to do this one step, and you check this condition every time. This is just a loop. Okay, so it's not going to be hard to implement this. I'll show code later, and as you'll see, almost all of the code is the setup of loading the stuff and then the printing of it afterwards. The actual code that doesn't work is a very, very small piece of code, and this is common. Okay, so there are a few things that I've not fully discussed yet. So I've not discussed this threshold here, and in general why this condition makes sense. Okay, there's another thing here. This is going to be called the step size. Okay, and I indexed it here by k, so we can talk about changing it at different steps. The simplest way is just to keep this fixed. Okay, so if this is confusing, you can think of keeping this fixed. And I think for what you need to do in this course, you can basically keep it fixed and you'll be okay. But in other cases, as we'll discuss later today, you don't always want to keep this fixed, and your choice in here or how you adjust this will determine how well this algorithm works. And then the important thing is this object here is it's the gradient. Okay, this gradient is the key thing here. This tells you how to update your state. Okay, this is what tells you how, this tells you how much, and this tells you when the amount of the update, the norm of the gradient, same thing as here, when the norm of the gradient is small enough, I can stop. Okay, so again, the gradient is the key thing here. Okay, so let's, so I went through some stuff on the gradient, but let me,
question.
Yep.
So we're doing this until the gradient of alpha k is less than some threshold. But
Yeah.
if we've already updated it, would we want to look at k plus 1?
Well, that would require, I could think of, if I were to implement this, maybe I would calculate this and I'd store it in a variable, and then I can check it down here.
Right.
I have to compute the gradient once every step. This is one I've already computed. This is one I'll compute next.
Gotcha.
So it's not so important. If you happen to, I haven't calculated alpha k plus 1 yet when I get to this checking point, right? So I could calculate here and then I could reuse it here.
Like one update more than threshold.
Yeah.
Gotcha.
Yeah. So one thing to keep in mind if you're implementing this, the most expensive part is probably calculating the gradient. So you don't want to do that twice here. It'll kind of double the cost. It's better to store this and then reuse it. Yeah. So and like asymptotically, they're the same runtime. So from an algorithm's perspective, it's not a big deal. But in practice, a factor 2 is a big deal in some cases. Yeah. And so this is the most time-consuming step of most of machine learning is running some form of gradient descent. This is where all the computation is. So fine, yeah, you can return alpha k or alpha k plus 1. You can do whichever one.
Right.
Yeah.
You just have to store alpha k and k plus. Because I'm assuming you're overriding.
Okay. Yes.
That's kind of what I was, I guess, trying to figure out.
Yeah. You can probably do that. Usually the space of storing alpha is not too big. I guess if it's like a really big deep network or something, it could be big and you wouldn't want to do it. But often the first time you run this, it's not going to go the way you expect, and you're going to have to diagnose something about it. And so storing all of the model parameters you've gone through before is usually useful to do that. If everything goes great, then if you're running inside of an algorithm, like as a lot of the black box functions for you inside of scikit-learn or or something, or SciPy, use, you know, what they use in there. You probably don't need to store it, but if you're kind of setting up something new, you probably want to store it at least initially until you're sure you're doing the right thing. Yeah.
So I'm confused about the stopping threshold and what it's actually checking.
Yeah. So we'll talk more about this in depth in a bit, and I'll try and explain why this is what makes sense to do. There are other things you can check here, right? There are other sort of conditions you can write here. This is probably the most common one, and I'll explain why it doesn't take a lot of time to compute this, because you've already computed this as a vector. You just have to take its norm, and why it makes sense to look at that. Okay, so I'll get to that. But I just want to review a couple things about the gradient. All right, so this is going to be a vector RD. Okay, and so alpha is going to be just the vector of the D. So partial derivatives, and partial derivatives are no more complicated really than taking a regular derivative. I just fix one of the coordinates as being the variable, and the ith coordinates that I'm dealing with, and the ith coordinate of alpha is the variable. The rest are constants, and then I just do the derivative like you've taken in a calculus class, and we'll basically just do polynomials in this course, right? So you should know how to calculate this. Okay, this is a vector. I also mentioned that the directional derivative, right, which is this nabla u. Okay, this is the derivative in so this direction u. So think of, I've got some function where this is the minimum, and I could think of kind of the height function is going out. So this is the Salt Lake, right? And as I go up the valley around it, it gets higher, but like down the valley. So the Jordan River runs down here to the Salt Lake, and then the Wasatch are coming up here, and the Oka on this side, right? So think of the height functions coming up, and if I'm at a point alpha right here, so this is a point in our D in this example, D is 2, then I can pick some, I can look at, so some direction u, and we'll say, what's the derivative, one-dimensional derivative now as I go in this direction u, and I'm going this way, right? And I care about, I'm not making a big jump out here, I'm making an infinitesimal small step in this direction. Is this going down or up? It's going down a little bit, right? So the derivative will give me a smaller function value here, but this will depend on this choice of this direction. This is also a vector in RD, and with usually you set the norm of u to be 1, because when you call the direction, I'm taking out the scaling function. Okay? So given the directional derivative, so this from the full gradient vector is just going to be just the dot product of this full gradient vector with u. And I take the dot product of these two vectors. So it tells me how much to weight each of these coordinates is what the dot product is doing. So it's telling how fast is it decreasing in this direction here. It could be negative, kind of as, and so forth. So given the gradient, I can get the directional derivative in any direction u by just taking a dot product. Okay, I'm the fastest, right? I want to figure out, well, I want to go down the fastest, and I'm going to use as a proxy the negative of what's going up the fastest. So I want to find the directional derivative that's as large as possible. If I take a one step, how far up? I want to go up the fastest. So I'm over here by the, this is in, what is it? Is this Draper over here? No, there's, I don't know all the same names, but I want to step up into the ochres. This direction will have me go up the fastest in some way. Okay? So if this way goes up the fastest, then I want to go down. I'm then going to step backwards. Okay?
Sorry, just to clarify here. So the way that we're getting U is just by taking like alpha and normalizing it to 1?
No, alpha is not normalized here. This is any direction. I can define this for any U. So this, I've not specified the right U yet. I've defined this for all U.
Oh.
I've defined something called the gradient here by just a bunch of these partial derivatives. That's basically saying if I put an orthogonal basis here, right? So the first direction and the second direction, this is, say, E2 and E1, I can define the partial derivative in x and the y direction. And that gives me this gradient vector. Now for any u, I can say, if this is a direction u in black here, I can say, what's the derivative? How much do I change if I go in this direction? But now I say, well, to go down, I should probably go down the direction which goes down the fastest. And I'm going to do that by finding the way that goes up the fastest, and by, because I assume it's locally differentiable, then going down the fastest is the negative of that. So I want to find the direction that goes up the fastest. Okay, so I want, what's that mean? I want the norm of this to be the largest possible. So I want to find the, so I want to move in direction u star, the norm of the directional derivative. Okay, so I want to maximize this norm, and I want to move in the negative of this direction. Yeah.
So when we're talking about U, we're just talking about a 1 unit of step, is that right?
Yeah, so think of it, I'm taking some step. It doesn't matter how big the step is. I'm going to, in some sense, I'm making it, in the limiting sense, arbitrarily small. I defined it last week Wednesday in terms of limits and so forth. And that's the right way to think about it. But I'm actually going to make a discrete size step depending on, depending on gamma over there. Yeah, but I'm going to define this in terms of infinitesimally small steps. Yes. Yeah.
Should the directional derivative be a scalar? Like, are we missing u next to it?
Yeah. So the directional derivative, this is a dot product. So it's a scalar. Yeah, so it's a scalar. So I just need absolute value. Yeah, thanks. So this is a scalar because I've reduced it to a one-dimensional problem. When I pick u, I'm just taking a slice through here, and I'm only looking at this one dimension. What's nice is even in high-dimensional settings where we're generally going to be working, it still looks like one dimension once I fix u. Right? So does that?
So is the directional derivative the projection of the gradient onto some vector u? Like, shouldn't it be a vector itself, or am I thinking something totally different?
I can multiply by u, and then if I put a u outside here, then I get the So at least according to my notes, maybe that there are other ways to define something, but I want to know the derivative in this direction. Once I specify direction, it's a one-dimensional problem, so the outcome here is a scalar. Yeah.
So the gradient is like the direction of fastest ascent. So we got at any particular point.
Okay, so the point is if I look at this now, I want to argmax this. It's a dot product at exactly the normalized version of the gradient vector. That's where it maximizes. Two dot products are maximized when they're pointing in the same direction. Yeah.
So then is the directional derivative, like the number we get, the magnitude of that fastest ascent?
Yeah. Yeah.
So
Well, no. The directional derivative is not the magnitude of the fastest ascent. It's the magnitude of the ascent in direction u.
oh,
In this
okay.
case, in this direction u, it's negative, so it's a descent. But the one that maximizes it, assuming I'm at a regular point of the function, which generally is the general case, so I will assume I'm at a regular point of the function, the direction which maximizes it is going to be the direction of the gradient vector, and that's going to be something positive. I'm going to be increasing in some way. Okay, so this is going to be the gradient vector here at alpha, is the blue one here. That's the direction of the steepest ascent. Okay? And if that's going up, then I want to go down, I go backwards. Okay? Okay, so once I have the gradient, that tells me the direction to move, the negative of that direction. Yeah?
So here you're normalizing the gradient. So like have it be length 1, is that true at the very bottom there to get u star?
This is u star as I've defined it here, yes.
Okay, so then in the algorithm though, we're choosing a step size with the, I don't know if that's lowercase Greek letter.
Well, this is the direction I move. I'm just going to actually use the gradient vector here,
Okay.
which means that if the gradient is larger, I'm going to take a larger step,
Okay.
irrespective of the step size.
That's just an extra multiplier on top of the magnitude of that gradient vector.
Yeah, and in fact, this turns out to be nice. It means if the gradient is big, I'm probably going to assume I'm pretty far up the hill, so I can take a big step, and I probably won't hit the minimum. Whereas if it's pretty flat, like right on the beach of the Salt Lake, it's pretty flat. So maybe I want to take a small step because I might almost be there. Yep.
Oh, sorry. So for to solve the argmax of u star, I don't know. I didn't catch how you got equals the gradient of that divided by the or not the absolute value, but the yeah. I didn't catch that part.
So yeah. So this is this denominator part here is because I need to enforce the length of it as 1. I'm just saying, I'm defining just a direction to move in to the steepest ascent. I just want to make the point that this is how you define a bunch of directional derivatives, which gives you, this is the gradient. It's defined with respect to coordinate-wise directional derivatives. And I can get any directional derivative with a dot product. And I want to go the direction, if I take a fixed step size, which way is going to increase the most. And it turns out, as with because it's a dot product, with any vector, this is going to be, probably want to take away these absolute value bars there. With any vector, this is going to be maximized when I set this guy the same as here. If this length of this is fixed, then this quantity is maximized when the right part is equal to the left part.
So any vector is maximized when it is the dot product of itself, basically.
Right. So if this is the direction, let's see. Yeah. So this is a general property. So this is v, which it turns out. Okay, but just some vector v. If I take any direction u, right, and let's say u, and I know the length of u equals to 1, then when I take the dot product, what's it doing? It projects it down onto u, and it takes this length. This is u dot v. Okay? Where this is any vector v. It's the length of the projection. Now, if I took the projection here, so it's orthogonal, right? If u is orthogonal to v, the length of projection is 0. That's not doing very good. That's going to be along this, along the isosurface, where this is maximized because it must lie on a circle here. Where it's maximized is if u is here, then the projection gets itself back. And I get the length of itself.
That makes sense. Okay.
And so to make the length 1, I need to divide by the length of itself. This is a general property of dot products, right? Right. So this is I mentioned this when I talked about dot products. They're a really cool kind of geometric operation. This is encoded in the dot product. So this is a proof that from directional derivatives you can get the direction of steepest ascent by using this gradient vector. Defined this way. Okay.
That makes sense.
Good. So this was just a rationale for why this vector we calculate this way is the right thing to use, but you can just use it. This is the direction. This is the definition of the gradient. You can plug it in here. This is the algorithm. Okay. This is just why the gradient is the right thing to use here. Yeah.
Is the direction derivative, is that the scalar that comes out at the very end? Or what exactly is the direction derivative?
The directional derivative is, okay, this is the limit as h goes to 0 of f of alpha plus h u. It's this, right? So this is a limit, basically the same way we define the limit in one-dimensional calculus, but now you're increasing by in some direction u instead. Okay, and that's the definition of the directional derivative. But it turns out if you have the gradient vector, then it's just a dot product with u.
Gotcha.
Okay. Okay, and that just tells you how much to weight each of those components. It's an orthogonal decomposition of this. This will look more familiar once we get to PCA and the dimensional reduction. We'll be doing more stuff like this, but I kind of previewed it in the linear algebra section. Okay. Okay. Good. So let's talk a little bit more about the ins and outs of the gradient descent algorithm. Okay. So we partially covered this last time, but this is why the gradient gives you the direction of steepest descent. And when you're at a steeper part, this is going to be larger, and you're going to take a larger step for a fixed step size parameter. Okay. Okay. So why does it make sense to use the norm of the gradient as the stopping condition? So I said I'm going to use the norm of the gradient is less than some threshold. This will determine if I stop. So the right way to think about this is the rationale is if alpha k equals r min alpha. Right, so if this is a minimum or just or is just a local minimum, then what should the gradient be? Then in this case, the gradient of this function is going to be equal to 0. Okay, one way of defining a local minimum is that the gradient is going to be equal to 0. Okay, so minimum, so if this is alpha star, then the gradient, one way to think of the gradient of a function, so if I have alpha, let me draw it up here first. If this is this is alpha k, then the gradient kind of tells me, well, there's some linear approximation here. And so this is the amount of information gain, the function gain at the gradient. It's kind of, there's this linear function I'm fitting. I'm assuming that it's a dot product with the direction u, so I'm fitting a linear function at this point. And I can consider all linear functions, so I find the one that increases the most. Okay, if I do the same thing at the minimum, the linear approximation should be flat. It's the minimum, which means that, and this will be in all directions, there's no way I can go down, so it has to be flat in all directions, which means that the gradient is going to be the all zeros vector. Okay, so, and which means that the norm of the gradient at the derivative here, the norm of this should be 0 at the minimum, or if it's any local min, but we're going to assume functions are convex. Every local min is the global min. Okay, so so if I'm at the minimum, the norm of the gradient should be 0, and it should be kind of, if we assume if it's nice, it's going to be smoothly kind of changing. It's going to change a little bit at a time, and that means if we're close to the minimum, it's probably going to be small, maybe less than some threshold. Okay, so if it's less than some threshold, I'm probably close to the minimum. Okay, so these are all the points that the alpha prime, or the norm of, is less than some threshold in this range here. These are all the points where if I look at the linear approximation through here, it's pretty shallow. And so I'm pretty close to the minimum, and function value and distance, I'll stop. Otherwise, I might never exactly get to the minimum. I might keep inching closer. So if you heard of like Zeno's paradox, one way of saying is that there's this rabbit that's hopping across the road. Every time he hops halfway from where he is to the other side, but he doesn't ever get there, right? Every half is getting halfway there. And so I might not ever get to the true minimum exactly. There might be numerical issues as well and imprecision. So when I'm close, this is a good sign I'm close enough, especially for convex functions, so I will stop. At least usually this is true. If it's not convex, some weird things can happen, but for convexity, it's a good proxy. And it's something I've already computed. I don't know what the true minimum function value is. I could have also done something like, well, if the function value is close enough to the true function value, well then I could stop then. But I don't know what the true minimum function value is. I know the true gradient norm, the minimum norm of the gradient is going to be 0. So I know if tau is something close to 0, then I know I'm close to the minimum in some way. So it's something I know is going to give me, it's going to be comparable to the properties at the minimum, and so it kind of makes sense. Okay. There are other things you can do, like if the amount of things I've moved has been small, but that'll be a direct relation of the gradient anyways. The smaller the gradient, the smaller I step. And that will also mean the smaller the function value is going to decrease by smaller. So it's pretty much captured in there pretty well. Okay, great. So let's. Okay, now let's talk about. Okay, so let's talk about the step size, and I'm recalled by my notes, a more common name for this is the learning rate. So this is gamma k. Okay, and so the so the simplest, maybe not the most common thing anymore, but the simplest thing to do, and in some places the most common thing is to fix, is kind of keep the learning rate fixed. Just pick some parameter and run with that with that learning rate. If I converge, great. If I didn't converge, look at the trace of the function values and maybe adjust it and just try again. Okay, and that's a pretty kind of involves a little bit of hand tuning on your part, but that'll be simple to do for your homework. You'll implement this, and for the most case, you can use a fixed learning rate, and things will work. If you choose the wrong one, you'll be able to see. I'll show pictures at the end of a demo at the end of the lecture today, and you'll see what happens with different learning rates. With the picture, in most cases, you might want to print out the function value or the gradient as well, and you can kind of figure out kind of what's going on by that also. Okay, so how to choose gamma, or in general gamma k. So as I said, the simplest is to guess and check, and I'll give you some visual tools to deal with that kind of later on in the lecture. These will work for two-dimensional functions, but you can kind of, once you get the two-dimensional function in your mind, you can kind of you'll get some sense of what to look for in higher dimensional functions, but just looking at the function values. All right, so but there are other. So if we assume more about the function, there are also kind of some special properties we can say about how fast it converges if we choose this right? So let me talk about some more general properties of the function. Okay, so the first is if we have a Lipschitz bound on the gradient. Okay, so we say a function g from Rd to, in general, Rk. K can be 1, can be d, can be something else. And then think of this as the gradient. That's why I use g. We say that this is L Lipschitz if for all P and Q in Rd, that G of P minus G of Q, if the difference in the function values is less than L times the difference in P minus Q. Okay, so what this says is that if P minus Q, if P and Q are two places I evaluate this function at, they change by a small amount, then the actual function value does not change by too much more. By some linear rate, it's controlled by the difference here by some linear rate.
Yeah. Is that G of P times G of Q, or is that G of P
Minus.
minus?
Yeah. So if the function value is, if k is 1, then this is just going to be an absolute value difference. Okay. So this means that and if this is on g, that's the gradient, that's the change in the gradient. That means it's the, if g is this, then this says something that the df u squared is less than L for all alpha and u. Okay, so it's saying something about the second derivative here. Means the Lipschitz is usually telling you something about kind of the first derivative, but we're applying it to the first derivative, so that's saying something about the bound on the second derivative. Okay. Okay. So how to think about this is going on is that in general the function will be convex. This might be f. What the first derivative tells you at some point alpha, the first derivative tells me something about the gradient. That's the norm of the gradient. The norm of the gradient is changing, and it's actually changing fast. Even if this is for a parabola. So they can change fast. As I get to really high regions, the norm of the gradient is changing pretty fast, actually. So I don't have a bound on this, but I have a bound on the I don't have a bound on the gradient. I have a bound on the change in the gradient. Okay, I'm saying if I go from alpha, this is equal to p, to another point q, and now I look at another gradient here. This is at p, that these two should be pretty close. If p and q are close down, remember this is RD, this is P, this is Q, and it says P and Q, if these are close together, then these functions should be close together too. Okay, they're not quite the same. The slope at Q is a little bit higher, but it's not that much higher. Okay, so another way of understanding this is bounding the second derivative. It means that at every point alpha, there's some parabola that I can fit here. The gradient gives me a first fit. This should be underneath. The gradient gives me a linear fit. But I can say that there's a parabola, right? This is a second order fit. I'm saying there's another parabola which lower bounds the blue function, which is f. Okay, and if I'm lower bounded by this green function, which is locally a parabola, I can fit a parabola everywhere where its second derivative is at most L everywhere, it's not changing too fast, then I can basically I can say that if I apply gradient descent on the blue function, I will converge no slower than if I would on the green function, which is my fit everywhere. And so basically, this implies up here that if I set gamma to be less than 1 over L. Okay, so and F is also convex. Then I will say that that after k equals c over epsilon, then I will have f of alpha star minus f of alpha 0 is less than some error parameter epsilon. So it has to be 1 over c over epsilon step. C is some large constant. C depends on basically f of alpha start minus f of alpha star. So if I start with a really high function value, then c is going to be larger. Okay, it's the number, I'm going to need more steps. If I start really close to the minimum, it's not going to take as many steps. So c depends somehow on this. I assume this is bounded by a constant. And then after, but it decreases at a rate, the error decreases at a rate which is linear. And conveniently, this is called quadratic convergence, even though this is a linear decrease. We'll see linear convergence in a second. But this gives me this quadratic convergence, means c over epsilon steps, I get epsilon error here. If I set the learning rate smaller than 1 over L. And I know what L is. Yeah.
G maps RD to RK. Is there significance in K there?
K in this case is going to be D. Because I'm going to get, this is the gradient function. L Lipschitz is defined more generally. I wrote the more general definition up. But think of K is equal to D in this case. Yeah. So that means in the 2 norm, the gradients are similar. They're similar in all partial derivatives. All directional derivatives are similar. In a 2 norm sense. Yeah. Okay, so that means if I have a L Lipschitz bound on the gradient, and in general I will, this will have to do with this will be depend on the coefficient of a squared term. If I have if I have a quadratic function, then then L will depend on the coefficients of the squared term. In some sense, this is the bound on the second derivative of a function. Okay, if I have this and I set the learning rate sufficiently small, then it will converge at this rate. C also depends on how small is gamma. If I make this really, really small, it's still going to take a lot of steps, because every step I'm just kind of making really, really, really small steps. So I don't want this to be I don't want to set it as small as possible, because then I don't go very far every step. Okay, but if I set it below here, I'm guaranteed to kind of converge in this way. Yeah?
Just to double check with this bound number, choosing like a step size, or keeping that step size, or reducing our step size
Yeah.
closer.
This one I'm still fixing the step size. I'll talk about decreasing the, well, I'm decreasing, yeah, I probably should have written step size up here. The step size would probably be the combination of these two. So the amount I move is going to be decreasing because the gradient will be decreasing.
Okay.
But the learning rate will be fixed. So the learning rate is fixed. The amount I move every time will actually be decreasing because the gradient will be decreasing because of this argument. Okay, good. So I know I will converge if the step size isn't too big. I'll show some examples later. What will happen if the step size is too big that this is going to break? So if I'm, let's say I'm in the Salt Lake Valley, I'm on the hookers, and I'm a giant, and I take a really big step size, I wind up on the loss edge, right? I'm not going down the back. So if I take a too big of a step from here, I jump way over to here. And then I take a too big of a step size, I'm up here, and then over there, okay? And that can go wrong. So it won't converge if your learning rate is too high. You'll kind of keep jumping over the minimum. So you kind of, this tells you if I set it less than 1 over L, where L is the bound on the second derivative, I will not step. I think this would ensure I don't ever overstep it. But at least I don't overstep it too much. If I went from here to here, I made pretty good progress. The next one will go down here, and I can do a zigzag completion. That still works. Okay, but okay, good. So this is kind of helpful. It says if it's convex, and it's bounded by a quadratic. If it is a quadratic, it's going to be bounded by a quadratic. So then, if I set the step size small enough, it will converge, right? So that's good. Okay. But this so far, I only used that it was convex. It turns out that if you can instead assume that it's strongly convex. Okay? Who remembers the difference between convex and strongly convex? Told you this was, I had to define this for some reason. Probably like, whatever. Right, what was the difference?
I want to say it was like there's only a single minimum. There's like it's like it's like 1 point. It's like a flat line that exists.
Yeah, so that's implied by being strongly convex, that there is going to be a single point which is at the minimum. A convex function, for instance, a line is a constant function is convex. It's not strongly convex.
Just to guess, there was a definition for convex where if you pick 2 points, the points in the middle are going to be less than or equal to those. They would be strictly less than.
Yeah. So it's the strictly less than property, right? So it's I had this property that f of alpha p plus 1 minus shouldn't use alpha here. Beta, or forget what, 1 minus beta q is f of p plus 1 minus beta f of q. And if it was convex, it was less than or equal then. If it's strongly convex, it's strictly less than. Okay? Okay, and on Wednesday, we'll see examples of convex and strongly convex functions. Okay, we'll see that basically if I use one data point, my function will be convex, but not strongly convex for fitting a high-dimensional model. It'll be underdefined. There'll be a bunch of equally good solutions, right? But if it's strongly convex, there's one unique solution. Okay, so if it's a strongly convex function, I can say something much stronger. Okay, and I'm going to say f is eta strongly convex. Okay, so it's eta strongly convex for some parameter eta greater than 0. Then I'm going to have the property that f of p is going to be less of f of alpha plus some linear approximation. This is a linear approximation at alpha. If I'm trying to, so let me write this up and then we'll draw a picture. And this is a second order approximation, a quadratic approximation. Okay, so this means it's eta strongly convex. And what's happening is that I'm going to have some function f here. Okay, and then I'm going to have a point alpha where I'm approximating, and I want to say some point p. And if I do a linear approximation, this is f of alpha plus, this is the linear approximation. I say I'm going to start at this point. This would be a zero order approximation, just being constant. right? A linear approximation means it's changing linearly as I change from alpha to p. I'm changing by this much. This is p minus alpha. So I'm moving this much in the direction of p.
Daddy,
Yeah.
I can't hear it.
That will give you every time. Okay.
Look at it.
Uh-oh.
It's over here.
Okay, it's good.
And here.
It's not working? Okay, maybe one of you guys can troubleshoot this? One of my teaching assistants will help you troubleshoot. Okay. The sound of your own kid's voice when you hear it in the middle of nowhere, it's like, whoa. Okay. Okay, great. So first order approximation here. I'm moving this distance from p to alpha, and this gives me a linear factor here.
Like last time, it's not how it was last time.
Okay. Octonauts is not working. Everything falls apart. Okay. Now I want to do like a second order approximation, like over there. But now this is going the other direction. So now I'm getting a second order approximation like this. Okay? Now the green doesn't show up very well. Okay, so it comes in a little bit. Let me try and, so there's another parabola on the inside. And this is a second order. It's got the constant term, the linear term, and the second order term here. And it's saying that I can always fit a parabola now with eta over 2 here as the coefficient instead of L over 2. This always upper bounds the function.
It only sounds like music, not
Oh, what's that?
words.
So this says if it's strongly convex, that means that there's in every direction I go, it's going to be parabolically increasing at least a certain rate, as well as decreasing. So the L Lipschitz bound on the gradient gave me a parabolic lower bound, and this gives me a parabolic upper bound, the strongly convex property. It implies there's some eta, if it's eta strongly convex, there's some eta where I can upper bound it with a parabola as well. So now if it has both of these, it's going to be sandwiched in between two parabolas here. Yeah, good. Okay, this one of them goes too low. This one is bounded by, has L bound. This one is eta bound. Right, and it's here because I want this to upper bound the second derivative, because when I take the first derivative, the 2 gets multiplied by the 1/2 here, and the 1/2 goes away. Okay, so this gives me an upper bound on the second derivative. Okay, and so now I can claim that if this is true, that if the gradient is going to be L Lipschitz, and F is eta strongly convex. Okay, and now I set the learning rate to be equal to is upper bounded by 2 over n plus L. So this is basically 1 over the average of eta and L. Right? So if I set less than 1 over L before, now I'm setting it less than the average of eta and L. So I'm approximating it by some polynomial, some quadratic one between these two bounds. Then I will get that rate of convergence. Okay, and then I'm going to say that after k equals c times log of 1 over epsilon steps, then I'm going to have that f of k minus f of alpha star is going to be less than epsilon. Okay, so if I know an upper and lower bound, then, and I can set the linear rate in between these, I can get this linear convergence, which means that it's going to take log 1 over epsilon steps. And the way to interpret this is basically every constant number of steps, a constant number of steps, I'm resolving one of the digits of precision in the answer. Right, or 1 bit or 1 digit of precision, depending on whatever the constant c is. Again, the constant depends on how far away I start and so forth. But
I can't really enter it.
okay, and I don't want to make it too small. Okay, so now this means that this works really fast. And for most of the problems we'll look at, we will get this rate of convergence for gradient descent. If we have convex functions defined by quadratics, if they're defined by squared error, which is quadratics, then we're going to have a function that satisfies these properties. Typically, we'll see, and that means we're going to, every step we're going to resolve basically 1 digit of precision. So it means we're really converging really quickly.
Does this also apply to polynomials like degree higher than 2 as well when you do like when you apply the same stuff we just discussed?
Yeah, so it needs to be, no. It needs to be upper and lower bounded by a polynomial degree 2. Right? And so if it's polynomial degree 4, it can be convex in the right region. But at some point it will be going too fast. So I cannot directly apply this.
Is so for this one I hear with this problem sometimes, is it kind of like almost like a binary type search where we're kind of since we know the upper and lower bound, we're kind of
well, so we're gonna do something not quite like a binary search to find it. Let me quickly tell you how to automatically adjust it, and then I'll show some demos. Okay. Yeah. So we want it small enough. We want it. This actually says I don't want it. Yeah, I want it less than the average between these, but I don't want it necessarily in between these. Right? I want it less than the average. So I kind of wanted to make it as large as possible while satisfying this. Okay, so I want to start maybe a little bit larger than I should, and if I notice things are going kind of wacky, then I want to decrease it. This seems like a pretty reasonable recipe. So I'm not, a binary search should be going back and forth a little bit. Typically, if you're, in practice you might want to do that, because you might accidentally pick it too small. Sometimes you just don't know. You might pick it too small, you're like, I'm not getting anywhere. I've run 100 steps, I haven't really changed that much, and the gradient seems to be fixed. So then you would increase it. But usually you would start large, and then you would decrease it at a certain point. And I'll give you a simple formula for doing that. Okay. So, I mean, in general, if I do something smarter than this, I will still get this convergence. So if I do like, there's something called, I should mention something else first. Okay. Okay, so the first thing to do is actually, I'll just mention this, is line search. Okay, and this is to actually basically, given this gradient at alpha, I want to find equals arg min of gamma of f of alpha So this says, well, once I know what the gradient is, I can just actually solve for the gamma, which is the best. I can solve for the best gamma. I can't necessarily solve for it, because it's not necessarily closed form, but I know f is convex. That means in any one-dimensional slice of it, it's going to be convex, right? So that means once you fix this gradient here, the relevant part of f is going to be one-dimensional, right? I had this higher dimensional drawing here. Okay, so I've got this higher dimensional drawing. I've picked a point alpha here. I've got the gradient direction here. So now I can restrict my attention to this one-dimensional function. This does not include the minimum. Okay, but if I can hit this point right here, I've done pretty well. And so, if the whole function is convex, then this slice of it is going to be convex. And I can just now solve for the gamma, which places me here, and search for it. So I can reduce it to a one-dimensional problem. And I can run, say, gradient descent here. I can do something that I don't need to be perfect, but maybe I want to do pretty well. There's something I outlined in the notes called the golden section search, which is like a binary search sort of thing, but allows you to do it over a continuous space and so forth. So once I have a one-dimensional problem, I can kind of pick it at each time. But I don't want this process to take too long. If this process takes a long time, I'm better doing something stupider and spending my time on doing more steps of the higher level algorithm than doing more steps on the small algorithm. So sometimes people do line search if they can do this fairly quickly or solve this one-dimensional version of it. But if this is complex, then that might not actually be that. So this is a common strategy to use, but it depends on the trade-off of the cost of doing the line search. Okay, there's another heuristic I want to mention called the adjustable rate. Okay, and this basically, or this is called, say, backtracking line search. And so this says has a parameter beta, which would be between 0.1 and 0.8, and we'll say 0.75 is a good guess. And basically, you have this condition that if alpha minus gamma, right? So if the step I was planning on taking, right? If the function value becomes greater than alpha okay, so if my learning rate was basically, if I remember, I had wanted it to be less than 2 over n plus L, right? So if it's larger, I'm getting a function value larger than I would have gotten with this, this quadratic approximation using the second derivative bound as gamma, right? If it's larger than that, then I'm doing something wrong. It means gamma is too large. So then I update gamma to be equal to beta times gamma. Right? If it's 0.75, I've shrunk it to 2/3 of what it was before, and I check this again. If this is not satisfied, I continue with everything. But if this becomes unsatisfied at any point, then I reduce gamma. And so this will, because it adjusts it at it reduces it by a constant fraction every time, you can argue that as long as you don't start with gamma to be way too big, and you don't start with alpha to be too far away from things, then I'm going to get this linear rate of learning. I'm eventually going to get to a value of gamma, which is going to be close to the optimal one, just below this threshold, so I get this guarantee, but not too far below that I take too many small steps. Okay, so this is, yeah. Okay, and so this expression basically comes from the same quadratic analysis here. Okay, running a little bit late. Let's do a demo really quickly, or maybe I can do it at the start of. Would you rather I do it now or at the start of the lecture next time and answer some questions? Okay, good. So we'll do the then, or how about you ask questions while I get stuff loaded? I'll just show you a picture, and then we'll go through it again.
Yeah, backtracking of them, like I understand if f of the next point in the sequence is greater than or equal to f of the previous point, that we've jumped. You know, we've increased the value of the function. So I don't understand the need for this extra term gamma over 2 magnitude squared.
Right. So this is saying that that I've so it's increased. So it's supposed to be actually decreasing, and it's saying it's not decreasing fast enough. Right? Yeah. Okay. I do know if this is larger than this. Yeah. Clearly, my learning rate was too big. Okay. But it's not just that. I'm not converging fast enough. I want to get this linear rate of convergence. I want to get a digit of precision every time. So if I'm not converging fast enough, I should be converging not just less than this, but less than this plus this quadratic term. And it's basically saying I'm overshooting on this quadratic term. I've jumped down probably maybe below. I've jumped to over here or something. I've gone from here and I've jumped down to over here. Too much. Because I've gone below what I would have above what I would have expected, or yeah.
I was just wondering, I don't mind like the way of thinking of the way to define these convergence bounds. You find a lower convergence bound and a Lipschitz bound, right? And then an upper convergence bound.
So Lipschitz, they're both. I'm saying basically this says the Lipschitz bound basically is a Lipschitz on the gradient. So it basically says it's lower bounded by a quadratic function. So they're both assume it's convex, and then to get convergence bounds, you want it to act like a quadratic function. If it's going to be quadratic, that's great. But if it just acts like a quadratic everywhere locally, then that's sufficient. Okay, and so the L-Lipschitz bound, it's confusing because this is the kind of the common nomenclature in the language. One is described by a Lipschitz bound, the gradient. The second is described by an upper bound on the second derivative. They're basically a lower bound on the second derivative and an upper bound on the second derivative. L is a lower bound, gamma is the upper bound, eta is the upper bound. And if you have both of those, which requires strong convexity, then you get the faster rate of convergence. And so if I do this adjustable rate, this backtracking approach, then I start big, and if I don't satisfy this condition, I decrease it. I will eventually get in the good zone, and I will get the linear convergence. Let me we'll go through this quickly, but I just want to put this screen down and show this to you. I think this will help with your mental picture, and then we can go through this again and answer more questions on Wednesday. But we'll go through the code later. But I started here. This is some function. This is the minimum point here, and I'll talk about drawing these functions. And I've done great this step. I've stepped this way, and it's curling in here. This is with a gamma of 0.2. I increase this to 0.3. Rerun this. Then it's going to get further along. I'm taking a bigger learning rate, a bigger step size, and it's getting closer to the minimum. If I take this to 30, which is going to be too big. Oh, that was way too big. Okay. 5. Okay. Still way too big. Okay, this is what happened with 5. So I started here, I jumped up over here, then back here, then back there, and eventually I got some numerical error and jumped off to the side. Oh, this with 1, let's say 0.75. Oh, well. Good. Yeah. So this 0.75, it's converging, but this step size was too big. This would not have satisfied the bounds I needed. It still converged because it bounced around and back and forth in a zigzag way. It worked, but this would not have satisfied these bounds. The bounds work when I'm kind of making the smooth progression. And if I do 0.4, this one worked pretty good. I probably hit there before I took 10 steps. Okay, so I'll go back through this in more detail on Wednesday, and I'll post this on the webpage. And this gives you a sense of what you'll do something like this for your homework.
When you have data between 0.1 and 0.8, that's just an example, right? Or is it?
This was, this is not something I'm super incredibly personally familiar with, and this is the guidance I read on the internet. Okay, it should be basically between a value between 0 and 1. That's not 0 or 1, right? It's got to be some constant greater than 0 and strictly greater than 0, strictly less than 1. I said, the guidance on the internet told me between 0.1 and 0.8 probably gives you how close they are to 1 and 0 and 1 will determine the constant in the convergence rate. And the 0.75 was recommended. Pick 0.75. It should work pretty well. And actually, probably you want to use probably one of these second order methods and things, little stochastic things we'll discuss later in class if you need to do it. We'll discuss that on Wednesday as well. So we'll discuss, but this is maybe part of the big picture.
Another thing, when that does hold true and you switch gamma, is it just for that step, or you keep gamma where it's at for the rest of the time?
Yeah, and then you keep gamma where it is, or smaller the rest of the time. Okay. I basically want to start with gamma that's too big and kind of keep adjusting it smaller as needed. Once I find a gamma which satisfies that condition, assuming it's actually a quadratic function or something like that, then I keep it that. If I make it smaller, it means my steps become, I'm wasting things by taking too small steps. Great. All right, so let's read in here. Solve the problem with food. Yeah.
I have a question. So I was just trying to think of like a learning algorithm using gradient stuff. I think this is I can't remember this one that so like